So let's do an example problem with conservation of mass. And but before we jump straight into that example problem, let's do a couple things first. So what's the plan for today? First, I'm going to recap conservation of mass, both what the equation is qualitatively and writing down the formal calculus-y version of it. Then, once we've done that, I'll clarify a detail in the conservation equation, and in particular, what this v dot n term looks like, i.e. this is the velocity on the boundary of the control volume dotted into a normal vector, an outward pointing normal. What happens with this v dot n term if one or more surfaces of our CV, of our control volume, is moving? Right, so what's the deal if our control volume is moving? Last time we didn't really talk about that, so we're going to talk about that now. And then the final thing is we're going to actually get to our example problem. And regardless of whether you're a novice at fluid mechanics or an expert at fluid mechanics, it's almost always useful to approach fluid mechanics problems with a set methodology, to have these steps that we all sort of go through, and if you follow these steps, then you're much less likely to make a mistake. You're much less likely to flounder around before getting to some helpful or useful result. So let's hash out what the steps for the example problem is going to be. The first thing we can do is organize problem info. For example, what are some knowns? What are some knowns in the problem? What are some unknowns? Etc. Right? And I'm going to use the convention that I've used before, where known or given parameters are going to be in blue, and unknowns, things that we're trying to solve for, are in red, and things that we haven't quite worked out are going to be in black. Right? So it's useful to sort of organize this problem this way. Almost always regardless of whether I'm doing an example problem or you're approaching problems for homeworks and quizzes, almost always the first step is going to be define a control volume. And it's not just slapping one down on the page, but there's a certain strategy to it. And I'll talk about some key pointers from the strategy to make things helpful. And then just as soon as we define this control volume, we're going to go ahead and break it. Well, break it up in a very sensible way. So we're going to break up our control volume sensibly, and there's some strategy to that as well that I'll talk about, as we're going through this example problem. Then, if you recall, conservation of mass has some integrals and derivatives and a bunch of mess in it. We're going to work out these integrals, and oftentimes these integrals, we're actually not even going to need to do a lot of integration. Sometimes we'll end up just pulling almost everything out of the integrals, right? Remember, if we have integrals, you can pull constants out. A lot of times we'll be able to pull out a whole ton of constants, so these integrals aren't going to be too bad. Don't panic. And once you've worked out some integrals on the right-hand side of the conservation of mass equation, we'll also need to work out the left-hand side, right, if there's any goofiness going on there. Then, once we've sort of done these integrals and worked out what's going on the left-hand side, oftentimes we might need to do a little bit of algebra to cancel, solve, or organize our results in some way. And then once we get to some final useful result that we hope will be what we were looking for in this problem, it's oftentimes good to do checks. To do checks at the end, and in particular there are two checks that we often like to do. Take a moment now, pause and ponder. What are those checks that we like to do? Well, pause and ponder. Well, my two favorite checks, check number 1, right? If baby you-know-who is going to be really upset if we don't do this check, we need to make sure that the units are okay on both sides of the equation or in any terms that we add. And the other check that we need to do is to see what happens to make sure our results still make sense. To make sense if certain parameters go up or certain go down, right? That our result goes up or down in the right way, based on our parameters going up and down. So this is the problem solving methodology that we're going to use when we approach our example problem in this class. All right, so let's do our quick recap of conservation of mass. So when we're doing conservation of anything, in general, it's the accumulation. So the rate of accumulation is going to be equal to the rate in minus the rate out plus the rate being generated. And it turns out for mass, we can formulate this. We can formulate conservation of mass this way. It's d dt of this whole term. It's the derivative of this integral of rho dv. And in this case, this is an integral over the volume of our control volume. And it's equal to minus an integral over the surface of our control volume of rho v dot n dA. And if you remember our control volumes, we sort of talked about it this way. We said n was basically this outward pointing normal. That's a unit vector that points outwards from the surface perpendicularly. We said v is essentially the fluid velocity at sort of any point on the surface, and it can be normal to the surface under some circumstances. It can be oblique. It could be tangential. We could have cases where we have no velocity at some parts of the surface, and this v dot n basically accounts for whether flow is flowing out, in which case the dot product is positive, or flowing inward, in which case it's negative. So this rate in minus rate out is equivalent to this integral. This integral basically accounts for the net ins and outs, and whether it's an in or an out is sort of automatically accounted for by getting this dot product right here. And our accumulation, the rate of accumulation, is essentially this, where the rate part is accounted for with this time derivative out front, and this integral right here is essentially integrating all of the mass in this control volume. So we basically add up all the mass in the control volume, and its time rate of change is going to be equal to the net mass in versus out, and that's accounted for the surface. And we know that for conservation of mass, mass can't be created or destroyed. There's nothing that can sort of spontaneously generate kilograms out of thin air. So we don't have, or I guess not even out of thin air, and out of a vacuum. So we don't have any generation in this case. So this is conservation of mass, and there we have it. So thus concludes our quick recap of conservation of mass. Let's clarify what this v dot n, for example, if our surface is moving. So let's say I had a control surface that looks like this, but in some mathematically prescribed way, I had this part of my control surface ballooning out with time. I sort of had some mathematical way to kind of describe how my control volume itself is changing, right? So this is not necessarily anything to do with the fluid flow, but just the way I'm defining my control volume is moving, right? So what if what if our control volume moves or changes? What if our control volume moves or changes shape? Well, we can still use this expression up here. It just turns out that for this V, you can't use the fluid, you can't use the absolute velocity. Or maybe more specifically, some velocity with respect to, some stationary point, right? Can't use absolute velocity with respect to stationary point, but rather this v dot n, the v used in this v dot n needs to be a velocity relative to the control volume, right? So if the control volume is moving and the velocity is moving just along, if we have the control volume moving in such a way that the velocity is also moving exactly with that control volume, then we don't really have any flow going into or out of the control, going into or out of the control volume, right? If the velocity and the control volume are sort of moving along exactly with one another, we don't really have flow entering or exiting the control volume that way. So in this case, v dot n would be 0 if we consider the relative velocity, right? So we can use this formulation. If our CV is moving, we just need to make sure to use a relative velocity of the fluid to the control volume in that case. So, and this will make an appearance in our example problem. So, stay tuned. All right. So, hopefully, I've clarified what to do if we have a case where we've for whatever reason decided to make our control volume a moving control volume, and in that case the key conclusion is you need to use a v relative to the surface of our control volume. So that's the key thing there. And I guess regardless of whether your control volume is moving or not, as long as you use a velocity relative to the control volume, relative to the motion of the control volume, you're good. So that's how this works. All right, now let's do an example problem. And of course, I'll start by organizing the problem info into knowns and unknowns and all that stuff. Of course, sometimes you would be given a problem where some of this information is organized for you already. So I'm going to sort of explain the problem and organize it sort of simultaneously. But of course, if you were solving a problem for yourself, you would need to do this kind of separate from the problem being given to you. So let's organize our problem info into knowns and unknowns. So recently there was this capstone design team, and they were designing a bioreactor. And this bioreactor had a reservoir that was going to store the cell culture media. And they had a tube going in, and they had some tube going out, and the cell culture media was basically stored, inside this reservoir. So there's some media, and they had some pumping in media, and then another pump or flow regulator that was regulating flow out. And this team wanted to know, hey, are there going to be circumstances where if we have, a difference in the flow rate in compared to the flow rate out, how is that going to change how rapidly the height of this fluid level in the reservoir changes, right? So, if I have some flow in and flow out, and if those two flow rates are mismatched, that's going to cause the water level or the media level to go up or down, right? And you can imagine, if you let that go on too long, if you let this mismatched flow go on too long, you'll overflow your media reservoir, and probably a bad idea, right? So bioengineers care about flow rates and matching flow rates and accumulation of fluid within some chamber, right? So we don't overflow our system. So let's just say that we knew some stuff about this problem. Let's say we knew a couple of things. So let's say we knew the area of the inlet, and let's say we knew the area of the outlet. So let's just call this A in, and we'll call this A out, and we'll treat these as knowns, right? I could take a pair of calipers and I could go and I could measure the diameter and, you know, and do all that stuff. And let's say we had some pump that was pumping in fluid from the inlet with some known velocity. Let's call it V in. And let's say, you know, we also had some other flow regulator or pump or something like that that was also pumping fluid out at some known V out. Let's say we knew the dimensions of the chamber that we were working with. So let's say there was a dimension B that's sort of like this kind of dimension sort of into the page, and let's say there's some width of the tank W right here, and let's also say that we wanted to know, and we could say at any given point the fluid has some level H in the tank, but most importantly what we want to figure out is, based on these flow rates in and out and all that stuff, what is the time rate of change? How quickly is this height going up or down, right? We want to know, is the height changing rapidly? Is it changing slowly? So our goal is what is basically dH dt, and essentially what is the time rate of change of the height of fluid in the tank. Let's say we're dealing with cell culture media, which is, give or take a little bit, pretty much the properties of water. So let's assume that the density of this material is known, and we'll just give it Greek letter rho for density. So we have all of these knowns about this system, and our goal is to figure out what is the time rate of change of the height of the fluid in this tank. All right, so what have we done? I would say at this point we've organized our problem info. We have a bunch of knowns about the problem, and we have a clear goal for some unknown that we're working for. Next step is to define our control volume. And let's talk about a little bit about the strategy for control volumes. So because we're going to use conservation of mass later on in this equation, we want to do conservation of mass in such a way that integrals are going to be as easy as possible, right? Who wants to do difficult integrals? No one, right? Anyone raise their hand? Nope, nobody raised their hand, right? And we also want to do it in such a way that dot products aren't going to be problematic, right? So if we do things in ways that dot products aren't going to be problematic, and we do things in ways that integrals aren't going to be problematic, then we're going to make our life as easy as possible, right? I'm not in the business of making anyone's life difficult, so let's try to define, let's be strategic about our control volume to do it in such a way that dot products aren't going to be too hard, integrals aren't going to be too hard, right? And overall, our life is going to be pretty easy. So the key strategy for defining a control volume is, one, to make some so in general, you want to make surfaces of your control volume coincident with parts of the surface that you have the most information about, or parts of the surface that you're looking for information about, right? So we want to make surfaces relevant and it's sort of information rich, right? So examples of surfaces that we have lots of information about are solid surfaces. For example, like the walls of this tank, right? If we do solid surfaces, then our velocity is 0, right? We don't have any velocity on a solid surface. So we have a lot of information about solid surfaces, right? Another good thing is to maybe define some of our surfaces to be at inlets or outlets. Right? So in this case, we have information about these inlets and outlets. For some problems, you might not have information about these inlets and outlets, but if you're looking for information about these inlets and outlets, then that will help you, right? So we can define things at inlets or outlets, and that will help us too, right? So if we make part of our control surface at inlets or outlets, that will help out. And in particular, this is going to be easiest and most helpful if we choose to define our control volume to be perpendicular to the velocity, right? And if we make our control surface perpendicular to the velocity, then this dot product is going to be a cinch, right? So that's going to be super easy. And then so inlets or outlets, and that's going to be helpful. And then another tip for defining a control volume that we didn't do in this problem, but we might want to do for future problems, so I'll just put it here just so you're aware of the strategy, is sometimes it's useful to make some parts is to make some parts of our surface parallel to streamlines, right? And if it's parallel to a streamline or to our fluid velocity, then V and N are essentially perpendicular to one another. So if the flow is parallel to a streamline, then V dot N is going to be 0, right? Because V and N are going to be perpendicular to one another if the control surface is coincident with the vector velocity of the fluid, right? So that's basically, it's easy to take dot products when things are perpendicular or things are parallel, right? So this basically makes our dot producting super easy. All right. So those are some tips for defining a control volume. So let's go ahead and define this control volume. So I'm going to define this control volume here, and I am going to break it up into a couple of pieces, right? So let's do that now. So I am going to make surface 1 the inlet. I'm going to make the control volume another part of my control volume coincident with the outlet. And the thing with the control volume is, I guess, when we're defining a control volume, it needs to be completely enclosed. So we can't have like bits and patches and sort of open holes in our control volume. It needs to be like a totally enclosed, like mathematically perfectly enclosed shape, right? We can't have like just part of a surface, right? So, I'm going to make part of my control volume sort of perpendicular to the inlet, part of my control volume perpendicular to the outlet. I'm going to make other parts of my control volume coincident with the walls of the tank, and I'm going to make another part of my control volume coincident with the top surface of the fluid. All right. So 1 is going to be inlet, 2 is going to be outlet. What I'm going to call 3 is going to be at the top of the fluid. And 4, what I'm going to call 4, is the solid of the tank. So I have I'm defining my control surface, and in this case, I'm kind of defining it and breaking up my control volume sensibly into 2 parts, right? So in this case, I'm sort of doing both of these at the same time. So I'm defining my control volume and simultaneously breaking it up in a way that's sensible. And it'll make sense in just a moment why I might want to break up this my control volume into a couple of pieces. So our control volume needs to be totally enclosed, but we can sort of break it up in a way that will make our lives easier. And what's the point of breaking up a surface? Well, if I have an integral of, let's say, a plus b, then the integral of a sum is the same as the sum of integrals. This is just like a, tale as old as time. This is pretty fundamental to calculus. So the integral of a sum is the same as the sum of an integral. So how does that help us? The way conservation of mass is formed is there's a single integral over the whole control surface, but I'm allowed to break up this integral into a couple of different pieces, right? So I have my control volume right here. I could break up this control volume into, part 1, part 2, part 3, part 4. And if I did an integral over 1 and added that to an integral over 2 and added that to an integral over 3 and added that to an integral over 4, then that would be the same as just doing the integral over the whole thing and getting some final result. So I'm allowed to break up my surface, and as long as I break it up in such a way that I don't have parts that are double counted and don't have parts that are skipped, then I can take this single integral and break it up into as many integrals as I choose to, or as many integrals as convenient. And we're going to take this control surface and break it up into these 4 integrals that I've specified here, because each one sort of has a different thing happening, right? The inlet has fluid kind of going in one way, the outlet has fluid going out a different way, so it kind of makes sense to sort of analyze these two systems separately, or two parts of our system separately. The solid walls of the tank, a fluid isn't moving at all, and then if I make another one coincident with the surface, that's kind of, there's sort of a different thing going on there, right? So in this case, I have a different thing happening with all 4 of these pieces of the integral that I'm going to do. So it makes sense to, instead of trying to integrate this whole thing all at once, I'm just going to break it up into 4. I'm going to break up the right-hand side of conservation of mass into 4 separate integrals, one for each surface, and adding them up will give an equivalent result. All right, so what's it time to do? It's time to start working out these integrals on the right-hand side. So let's do it. Let's plop down conservation of mass, and let's start working things out. So conservation of mass is d dt of the integral of rho dv, and this is equal to minus an integral over the whole surface of rho times v dot n dA. We'll just carry through the left-hand side for the time being. And we said, hey, we're going to break up this integral into four separate parts. So when I do this integral, I'm just going to do an integral over surface 1 of rho times v dot n. And hey, wait a second. Here I drew rho in black, but if you go back to our problem statement, we're going to treat density, right? The density of the media, that's a known parameter in this case. So we can treat rho as a known constant. So let's go ahead and change rho over to blue to reflect the idea that we know it. And then we'll have v dot n for surface 1 dA. And then we're going to have minus an integral over surface 2. Rho is known as well on surface 2. dA. We're going to have an integral over surface 3 of rho v dot n dA, and we're going to have an integral over surface 4 of rho, v dot n dA. Of rho v dot n dA. All right. So we still have the same left-hand side, right, which I'm gonna just sort of fully get out of the way here. So let's start thinking about what some of these dot products are, and kind of squaring them away. So let's look at surface 1 first. So I'm going to go back to surface 1, and let's zoom in a little bit on surface 1. So if I think about surface 1, my velocity, v in, is kind of entering the control volume this way. And let's just assume that v in is uniform. I guess we could maybe take this as a given. We're going to assume that this is uniform. And next lecture, or I guess not next part of lecture, but the next lecture entirely, we'll deal with velocity profiles that are variable. But for now, let's just do a simple case where we have some uniform velocity at the inlet. Right? In this case, we have v in going this way. But what direction does my outward pointing normal point in this case? Well, the velocity is going this way, but my outward pointing normal is going to point this way, right? So in this case, n points this way, and v in, my v, points this way for surface 1. So what is the dot product of, what is this dot product, v dot n, for surface 1? So I'll give that to you as a pause and ponder. So pause and ponder. What is v dot n for surface 1? All right, so perhaps you've paused and pondered long enough. So we have surface 1 here. We still have rho. In this case, v dot n is simply v in, but it's minus v in, right? If you have vectors pointing in opposite directions, their dot product is negative. N is a unit vector, so a unit vector dotted with a other vector is just going to give the magnitude of that vector. But in this case, they're opposite, so it's minus 1, right? So in this case, v dot n for surface 1 is going to be minus v in. And we still have this dA that we haven't yet totally dealt with. So in this case, we have d. All right, now we have surface 2. We still have rho. Perhaps you could pause and ponder. What is v dot n for surface 2? Well, perhaps you've paused and pondered enough. In this case, v out is sort of pointing out this way, and n for surface 2 is also pointing out. So in this case, v out and n, you're just taking a dot product of a unit vector that's exactly in the same direction as this other vector, so that's just going to give the magnitude v out right here. So v dot n, the dot product of those two vectors, is just the magnitude of v out, and it's positive in this case because they're pointing in the same direction. So here we just have v out for our v dot n for surface 2. And we still have this dA that we have yet to deal with. All right. Now we have surface 3, and let's talk for a little bit about surface 3. If you remember, surface 3 is the very top of our that surface of fluid, and we defined it so surface 3 moves. So surface 3 moves with our fluid. So take a moment now, pause and ponder. What is v dot n going to be for surface 3? Well, v dot n, if you remember from the earlier parts of our notes, in this case we have a moving. In this case, part of our control surface is moving, right? Our control surface is moving along with the fluid, and we anticipate that the height of this fluid could be changing. So we don't exactly know how it's changing, but we've said, hey, however it's changing, however that may be, this surface is the control volume is moving with this surface. So if the control volume is moving with this surface, we need to consider, hey, what's going on with any relative velocities? But if we say, hey, however this surface may be moving, if it's moving with the fluid, there's no relative velocity. There's no relative velocity of the surface and the fluid, and if there's no relative velocity between our control surface and our fluid, then the relative velocity of the fluid is 0 with respect to the surface. So in this case, along surface 3, V is 0. V is 0 because there's no relative motion, because we've defined our control volume to be moving with the surface. So 0 because CV moves exactly with fluid. So there's no relative velocity. So in this case, our V dot N is 0 because our relative velocity is 0. And we have dA. And then we have surface 4. So take a moment now. Remember, we said surface 4. Surface 4 is the solid walls of the tank. So take a moment now, pause and ponder. What is V dot N for surface 4? Well, if you guessed that, along solid walls, unless these walls are like porous or something like that, or there's fluid leaking out through the wall, right at the wall, right at a solid wall, fluid's not going to be jumping through there. Fluid can't be jumping through a solid wall. So if we have a solid wall, fluid's basically going to have 0 velocity at a solid wall. Fluid can't just penetrate through a solid wall. So in this case, velocity is 0 dA. So what does that mean? We can get rid of these two integrals pretty conveniently because they have a 0 term somewhere in there. Nice. All right, so what can we do? Well, now we're in the process of working out our integrals on the right-hand side. So we still have a little bit more work to do before we can get all the way there, but we've made a lot of progress subbing in this somewhat confusing and not particularly intuitive calculus-y stuff. We're now getting it as much as possible in terms of given and known problem parameters. But we still have calculus to do, right? So what do we need to do? Well, a lot of my favorite integrals are the integrals where I can pull as much stuff, as much constant-y stuff out of the integrals as possible. So what might enable us to pull some of these things out of the integral? Well, we can pull density out of the integral if our fluid is homogeneous, right? i.e., if it's not like, some case where we have like one type of fluid here and a different type of fluid here, kind of all flowing through this surface here, right? If we're basically assuming that it's pretty well mixed cell media, so it's the same type of fluid no matter where I am over this surface, right? So if the fluid properties aren't varying over the surface, right? If the fluid is homogeneous and incompressible, if the fluid's homogeneous and incompressible, then with respect to this surface 1, density is a constant, so it can pop out of the integral. And we could make the same argument here. If we have a homogeneous fluid, then density equals a constant. We can make further simplifying assumptions. If you look back, we said, hey, we're going to assume that across this inlet, our velocity is a constant. And in this case, in that case, we can pull V in out if we have a uniform velocity profile. So if we have a uniform velocity profile, then we can just pull it out, right? It's a constant over the area of surface 1, right? And we can pull out this. No, so V in doesn't need to be the same as V out, but just with respect to surface 1, V in is a constant that we can pull out. And just with respect to surface 2, V out is a constant that we can pull out. So that means we can make considerable simplifications to this to the right-hand side. So now we have minus the stuff that we pulled out of the integral. So we have minus rho times minus v in. And now we just have an integral over surface 1, where the only thing left in the integral is dA. And then we have minus rho v out, and then an integral over surface 2, where the only thing left in this integral is dA as well. Nice progress. So, how do we deal with these integrals where it's just dA? Well, if you remember, and if you remember back to high school calculus, if you had an integral, let's say dx, if you just had integral dx, you could kind of imagine this as like an integral of 1 dx. And if you integrate 1 with respect to x, then you get, you know, x. I'm neglecting the plus c for here. But, right, if you integrate dx, you get x. In this case, if you integrate dA, you get area. And in particular, you're integrating over surface 1. So in this case, if you integrate over surface 1 dA, then you get the area of surface 1. Right, so it's like integrate dx, you get x. In this case, you integrate dA, you get a. And instead of like dealing exactly with like whatever these limits of integration would be, even if you could even properly define them, you know, just know that if you integrate dA over surface 1, then you get the area of surface 1. And for our problem, the area of surface 1 is a well-known constant, the area of our inlet that we could put right here, right? So in this case, the integral over surface 1 dA is just equal to the area of our inlet. So what does that mean? We can make even more simplification to the right-hand side here. What is that going to look like? So now our minus rho times minus v in times integral over surface 1 of dA is just going to be rho v in, area of our inlet. And then our second term, we have minus, we have rho v out, they're still out here up front, and then integral over surface 2 dA, well, that is a well-known constant, whatever area of our outlet we have. Awesome, so what does this mean? What does this mean? For this problem, we started with something that was kind of messy, a little bit messy, a little bit calculus-y, not necessarily very physically intuitive, this whole right-hand side of our equation here, and that's simplified to things that we could get entirely in terms of knowns. And what is this? This is essentially the net mass flow rate. This is essentially the net mass flow rate into our control volume, right? And you can see, you know, if we have more mass in than mass out, then that's going to result in some mass, you know, it's going to result in sort of an imbalance that's going to be accounted for by more mass accumulating in our control volume. So what do we need to do now? Well, I would say we've successfully worked out the integrals on the right-hand side. Great. Now we need to work out the left-hand side. So stay tuned. So let's work out the left-hand side. So left-hand side is this derivative of an integral of rho dv, and this is an integral over the volume of our CV. So this is the left-hand side that we've kind of been carrying along the whole way here. So let's work on a fresh page. So dt of an integral of rho dv is equal to, now it's equal to this right-hand side, which is entirely in terms of known constants, which is great. So we have rho times v in times a in minus rho v out times area of our outlet. So if we can work out this left-hand side, you know, then we can start working out more about this problem. So let's start working out here. Well, we made, last time we said, hey, when we were working out the right-hand side, we said our fluid is homogeneous and incompressible, right? So if our fluid's homogeneous and incompressible, it could come out of these integrals because, density is basically constant, right? If density is constant, it's not varying across the inlet. But, if we have this cell culture media that's well mixed throughout the entire thing, in that case, it's not varying just across the inlets, but it's also not varying over the whole volume, right? So if we have this case where our fluid properties, and in particular our density, is not varying over the whole volume, it can come out of this integral, right? So if density does not vary over our control volume, then we can pull it out of the integral. And if density does not vary with time, then it can be pulled out of this derivative as well. So, in some problems you might have spatial variations in density, in which case you wouldn't be able to pull it out, but in our case we can. And in some problems you might have density varying with time. In our case, density doesn't vary either with space or with time, so we can pull it out of the spatial integral, we can pull it out of the time derivative, and it can be plopped all the way up front here. And we can treat it as this known blue constant rho that we have here. So now we have rho dt of an integral dv over volume, right? And remember, I'm using this v with a cross through it to distinguish volume EVs from velocity EVs that I have over here. And our right-hand side is still the same. Can we make any simplifications to here? So I'll pitch that as a pose and ponder question. Can we work out, we'll deal with the derivative later. Can we work out what this integral dv is? So pause and ponder. Consider, can we make any progress towards that dv? Well, perhaps you've worked it out. An integral dv over the whole volume of the control volume. In this case, this is just equal to the volume of our whole control volume, right? If I integrate dv, then I get v. And if I've integrated over the volume of the control volume, then that's just whatever volume that control volume happens to be. Can we express this volume in terms of known parameters? Why, yes, right? If you imagine, I've sort of drawn a rectangular reservoir here, so the volume of our control volume is just the width times the depth times, well, I guess the width times the length times the depth, which is w times b times h. Awesome. So volume of our control volume, in this case, just the stuff within this derivative is now going to be width times length times depth. Okay, but that's still within this time derivative here. So let's now plug this volume of the control volume in. So rho d dt of w times b times h is now equal to the right-hand side. So rho b in a in minus rho v out a out. All right. Well, if we think about this container here, unless this is like a stretchy container or flexing or moving in some goofy way, W and B, those should both be constants with respect to time, right? So if these are not varying with respect to time, then we can pull these guys out of the integral as well. And what does that leave us with? That leaves us with rho times W times B. H, of course, has to stay in here. Why? Because we anticipate that if these flow rates are not balanced, then the depth could be changing with time. And ultimately, what we're looking for is an expression for dH dt, but we have it here, right? We have d dt of basically just h left in there. So, we got it. dH dt. Awesome. And this is equal to the right-hand side. That's entirely known constants that we've been dragging along this whole time. Rho times v in times a in is rho v out a out. All right, we've made progress. All right, so what are we going to do? I would say we've worked out the left-hand side, but we still have a little bit of algebra to do to sort of cancel some stuff out, solve, and organize our results. And ultimately, what we said we were looking for was this expression for dH dt entirely in terms of known or given problem parameters. So let's do it. Well, we can just divide everything by rho times W times B to solve for dH dt. If we notice, all of these terms actually have rho, so we can just divide out rho straight out, and then we have in the numerator v in a in minus v out a out. And in the denominator, we have W times B right there. All right, success. So I'd say now we've done some algebra to cancel, solve, and organize our results. Now, let's do some checks. First, we want to check units, and then we want to make sure that our results still make sense if our problem parameters go up and down. So let's check units. If we think, what are the units of dH dt? So pause and ponder if you want. Do the units work out for this? Well, hopefully you've paused and pondered. dH dt, this is essentially like a velocity, right? It's like dx dt, or velocity. You know, the numerator would have units of meters, the denominator has units of seconds. If we think about it, v in times a in, well, v in is going to have meters per second because it's a velocity. A in is going to be meters squared. And v out and a out also have units of meters per second times meters squared. In the denominator, w is meters, b is meters. So we get meters times meters squared over seconds divided by meters times meters. In this case, this is meters per second, which was the same as what's on the left-hand side. So units check out. All right. Now, let's do our final sanity check. If I think about v in and v in times a in, if I think just about v in a in, then this is essentially a volumetric flow rate. It has units of meters cubed per second, right? So in a sense, this is our volumetric flow rate in and our volumetric flow rate out. If our volumetric flow rate in is bigger than our volumetric flow rate out, then the numerator is positive, so dH dt is going to be positive. And physically, that's consistent with whatever result we have here, right? If our volumetric flow rate in is bigger than our volumetric flow rate out, then that must mean we're accumulating media inside our chamber. So that media depth has to be increasing in order to account for the extra fluid going in compared going out. And of course the converse is true. If V out, right, or if our V out A out, if our volumetric flow rate out is bigger than our volumetric flow rate in, then the fluid level in the media is going down. So that means dH dt must be negative. If we have an imbalance in our volumetric flow rates, then dH/dt is going to go up and down more slowly the bigger the tank we have, right? If we have a really wide tank and I have a flow rate mismatch, it takes a lot more fluid to raise the level of a really big tank, of a really wide tank, than it takes, like a narrow graduated cylinder, right? That the fluid level would jump up or jump down very quickly in a very narrow graduated cylinder compared to a wide fish tank or something like that, right? So it makes sense. The bigger the width and sort of the bigger the the area, the size of our tank, that's going to make dH/dt go up and down more slowly for a given flow rate mismatch. All right, so I would say our sanity checks also check out. Problem solved. So thanks for listening, and good luck with your study of fluid mechanics.